So, hello again. We're back. Hello, everybody. We're back for the second day of this year's Software-Defined Radio Academy, and for technical reasons, we had to postpone one talk. The speaker here now is Adrian Musceac, in the picture below me. Hello, Adrian. Thanks for coming in today. And I would like to present Adrian to you. So Adrian is a Romanian amateur radio operator holding the call sign Yankee Oscar 8 Romeo Zulu Zulu, and is a Linux developer, a Linux software developer, and he's been interested in software-defined radio ever since he discovered GNU Radio around 2007, quite some time ago. These days, most of his radio contacts are made using his own SDR application described in this talk, and he's here to share his experiences. So we're going to play the pre-recorded talk. For the video team, please go ahead.
Hi everyone, my name is Adrian, and it's very nice being back here at the Software Defined Radio Academy 2021. Today I would like to talk about the GNU Linux multimode SDR transceiver application using GNU Radio and having voice over IP functionality built in. So, as far as a brief introduction of the GNURadio Link application, it is a small application which I have developed as a multimode SDR transceiver for Linux. It is free software, and it's using the GNU Radio C++ API for digital signal processing. User interface, which you can see in the picture on the right, is written in Qt. It is very similar to GNURadio. It basically uses the same graphical widgets which were kindly granted the permission to use them by Alex Chete, the author of GNURadio. The application is mainly focused on digital voice communication as an amateur radio experimentation tool. It allows communication with digital voicemails. It also supports analog voice communication with FM, AM, SSB, and it also has a video mode and an IP protocol data transmission mode. One of the core features of the application is that it bridges audio from analog digital radio, basically the SDR, towards the IP network. This allows the radio to be connected to various desktop or LTE mobile terminals, and also other radio sites which are using the GNURadio Link to transmit or receive signals. The development cycle is aligned with Debian Bullseye, so this means that you can expect any Linux distribution which is derived from Debian Bullseye will be able to build and run the application. It is also using some versions of the libraries which are listed below, in case you are interested. Now, a little something about the technical features which are built into GNURadio. First of all, as an application, it is compatible with devices supported by GNU Radio LimeSDR, and also devices supported by SOPI SDR, the other main device compatibility layers. Among others, the USRP, the ADALM-Pluto, which is commonly known as the Pluto SDR, the LimeSDR, the RTL SDR, the Blade RF, the Hack RF, and other devices which may or not be supported as well as the ones listed here. It has semi-duplex and full duplex operating modes, depending on operator selection, of course. It also has voice activation for external applications like WSJTX, which I have presented last year, also here at the Software Defined Radio Academy. The application allows transmit-receive switching and supports various external amplifiers and filter chains by using USB relay boards, which have the FTDI chipset on board. So it will be able to control up to 8 relays from this type of USB relay boards. The operation can work with in split mode and with repeater mode. It also allows mixed operation, which means that we can transmit digital voice signals and receive analog signals, and also vice versa, receive digital and transmit analog, either in semi-duplex or in full duplex mode. It also has support for audio recording using the free lossless audio codec. It has very basic remote control interface, which can be accessed either via Telnet or via Mumble text messages. It has memory channels, very basic headless operation mode, which means it doesn't have graphical user interface. And it can also operate in a repeater mode, which means that it can retransmit any signal which it receives, but only in full duplex. So the software-defined radio must have the duplex capability. It also has support for forward error correction in digital voice modes, video, and IP protocol transmission using the convolutional encoding, which is a very simple, basic forward error correction, but it's adequate for most purposes. It can work with multiple sample rates from 1 megasample per second towards 30 megasample per second for both receiving and transmitting modes. Like I said, one of the core features is voice over IP radio bridging using the Opus audio codec and the Mumble voice over IP protocol. And as far as compatibility with various Linux sound systems, it uses the Qt audio API and also the Qt video API, which makes it compatible with a wider array of Linux sound systems like Pulse Audio, ALSA, and also various types of video devices which are supported on Linux. And now moving on to the digital signals which can be transmitted and also received with the application. It can operate with digital voice and text data by using the FreeDV modems. I'm sure most of you are aware of FreeDV as quite a famous digital voice mode, which was created by David Rowe VK5GR. And this SDR transceiver also can transmit standalone codec 2 with various modems. You can see here, for example, waveforms for DQPSK, transmitting codec 2 and transmitting Opus digital voice, and BPSK, binary phase shifting, phase shift keying, and also frequency shift keying, either to PSK and 4FSK. Digital voice is using codec 2, like I said, at 1,400 bits per second, or for a better quality, let's say, sort of a wideband audio mode, it can use the Opus codec at 9,400 bits per second. Of course, this means that the signal will have a larger bandwidth than, let's say, one of the FreeDV waveforms, which are depicted here in these images. As far as FreeDV, it supports FreeDV 1600, FreeDV 700C, 700B, and 800XA, which are, most of you are probably familiar with these modes, especially 700B, which is quite popular for shortwave communication. Since the application can also transmit analog signals, this is a very brief list of the analog waveforms which it supports. First of all, FM mode in a channel of 12.5 kilohertz. Also narrow FM at 6.25 kilohertz. It has support for coded tone, coded squelch encoders and decoders, which are blocks in GNU Radio. The SSB mode, it is developed using the continuous envelope SSB transmitter, which is a GNU Radio out of tree module that was developed by Ron Economos, W6RZ. This mode has some very interesting features because it ensures that it does not exceed certain levels, causing clipping and signal splatter, which is very useful for SSB. It also supports the IM amplitude modulation mode. This is a very basic implementation. It's not very common in amateur radio. And it can also receive wideband FM for broadcast radio reception. In order to operate on FM repeaters, it has configurable repeater shift. So you can define your own repeater shift, and in semi-duplex mode, it will be able to operate on repeaters by changing the transmit frequency as the push-to-talk button is pressed. The semi-duplex mode is standard, which means that you have to press push-to-talk in order to be able to transmit the signal. But it can also operate in full duplex mode, which means that reception of the signal is not cut out. You can either monitor your own transmission or serve as a very basic repeater in this mode, because the application will just forward any signal it has received into the transmit port of the SDR. Another feature is the audio compressor. This is something that is very useful for the SSB mode, and is also usable for the digital voice modes, because the audio compressor can operate also both on input and on output. Other features are audible end of transmission notification for FM modes and audible timeout timer notification, which can be configured with a variable amount of time to either cut you out from transmission or to give out this audible notification in order to let you know you've exceeded your time on the air. Moving on, the core feature of QRadioLink is the voice over IP bridging interface. This bridging interface is designed so you can link your software-defined radio with an IP network and be able to communicate between radio nodes using the IP network and a server which serves to kind of like a reflector in order to push the audio samples towards all the clients which are connected. This can connect the transceiver with either desktop or LTE mobile clients on the same server, and obviously on the same logical channel. It has a client-server star architecture, which is depicted here in the picture on the right. It has this core server, which operates on the IP network. It can operate either on the same computer as QRadioLink operates, or it can be on a completely different computer. But this server allows connecting desktop clients, which there exists a variety of clients for the Mumble protocol, either desktop or possibly mobile. So you can use this voice over IP protocol with mobile phones, LTE mobile clients. There is server-side logical channelization, which means that users can be divided into talk groups, and the user can join or leave a talk group as he pleases. In order to transmit the voice over the network, the Mumble voice over IP protocol with Opus as an audio codec is used. This protocol, besides the audio frame, also has in-band signaling. So you can transmit text messages and also various commands which operate on the server or on other clients. For the radio signal, there is no call setup overhead, which means that once a radio signal has been received, audio is almost instantly propagated over the network, and PTT audio is activated on the other side. So there is very little overhead, no call setup, no time required to make a connection, no dialing involved. Latency is brought about mainly by network latencies, which can have significant values in case of LTE networks, for example. Also transcoding, because if let's say one of the software-defined radios is transmitting and receiving a digital signal, there might be some transcoding required from, let's say, codec 2 towards Opus, or from an analog signal waveform towards Opus packets, which are then sent over the network. Digital software processing also adds some latency, which may not be very small. This is latency which cannot be overcome. But the overall figure is around 400 to 600 milliseconds for an LTE client round trip, which means that by using a mobile phone, I am able to remotely operate my SDR transceiver, receiving and transmitting using push-to-talk on the LTE client, and have a delay of around half a second for the complete round trip. This architecture also allows radio server-to-radio network bridges, which means that you can have two radio sites in two separate locations, and one of the radio sites will receive a signal retransmitted over the network to the other radio site, which will then rebroadcast the signal. And this is valid for all the clients connected to the same talk group will also retransmit the same signal. The audio is bidirectional duplex, and the IP bitrate is flexible, so it can be configured within some values inside the application. Another feature of GNURadio is the video transmission mode, which is a very simple implementation. It doesn't try to compete with DVD standards. It has around 10 frames per second. The video frames are transmitted directly after capturing and encoded using the JPEG video codec. Voice is also transmitted and is encoded with the Opus audio codec at 9,400 bits per second with a constant bitrate. Audio frames are around 100 milliseconds long. The modem which is used to transmit the video signal is 125 kilosymbols per second VQPSK modem, which fits in a channel of 500 kilohertz, and it has half-rate convolutional code for their operation. Video frames are also checksummed in order to avoid spurious decodes and errors which might creep up in transmission. And the capture backend is Qt Video, which requires some GStreamer plugins, and it uses the system default video device, which is the one which is detected by GStreamer backend. This pretty much completes the description of curating and the feature of this small application, which I wrote. And in the end, I'd like to thank a few people because writing this software and experimenting with it would not have been possible without them. Nathan Bottoms, A4HS, is the Debian GNU Radio and 3DV integration developer, and is also doing the maintenance for these software packages. Alexander Chete, Oscar Zulu 9, Alpha Echo Charlie, has kindly granted me permission to use some GPRX widgets and some code in order to avoid duplication in the application. Also, Daniel Esteves, YO8RZZ, his open research and his publications were used in the development of the application. David Rowe, the author of Codec 2 3DV, and also has given me very valuable DSP advice. Marcus Miller, he has provided me with the GNU Radio architecture and DSP advice. Stephen Sostrom, he has been testing and providing documentation for Raspberry Pi OS integration. And of course, the GNU Radio and amateur radio communities, including everybody who participated in testing, bug submissions, feature suggestions for this application. If you want to read more about this topic, you can head over to the website at http://curadelink.org, and the code is available at GitHub at Curadelink project. Now, bear in mind this application is currently not considered very stable. It hasn't reached yet version 1, so there are still, I think, plenty of bugs or issues to solve. But it has been suitable for me in the last years or so. I have been using it almost exclusively to operate in amateur radio bands. And this pretty much completes my presentation. Thank you very much for watching, and hope to talk to you later. Bye-bye.
So, Adrian, thank you very much for this very insightful talk on your own application. Very, very interesting. That's particularly interesting because many people are actually thinking about having kind of a remote station. That's a very common discussion since we're thinking of high noise levels, particularly in big cities. So the question for many people is to place a receiver outside in the countryside, like we're here, right? I didn't tell you. I think I didn't tell you where we are right now. We're in the middle of nowhere, north of Munich, out in the countryside, and this is actually a very nice environment. When I look outside the window, there are cornfields. Of course, the window is blinded now, so that we don't get stray light. But out here, we actually have a very, very silent, high-frequency environment, and this is what many people want to have. And I mean, I tend to say for the legal limit, or a kilowatt in the city, for the legal limit in the city for transmitting, the power amplifier doesn't care for the noise level. It doesn't matter. But if you have a receiver and the noise floor is very high because of many power supplies around there, that's really a big problem in the city. So many people are really interested in having a receiver out in the countryside and being able to use it interactively and possibly also to transmit. And so this is why your developments are really very, very interesting for sure to many people. So there have been a couple of questions here in the chat. And Michael, if you want to raise your own question.
The first question is an icebreaker. Is there any recommendation how to put the 9,400 bits per second from the Opus codec into a shortwave radio channel of 2.5 kilohertz? Are there any ideas, or how could it be used for shortwave radio? Couldn't it? Or isn't it only FreeDV?
I think Daniel Esteves can actually answer that question better than me because he's been working on 16 or 32 amplitude PSK modulated mode for the Quebec Oscar 100 satellite. So he would actually put an even higher bitrate over the channel than this is the modem I used was just for testing the Opus codec for a radio channel. Basically directly forwarding the audio frames coming in from the voice over IP connection towards a radio channel, which is similar in bandwidth as FM, regular FM modulation. But yeah, there are definitely ways to fit that into a SSB bandwidth type channel. And like I said, Daniel Esteves is actually working on that. Hopefully, he will give us talk about that very interesting high bitrate mode for Quebec Oscar 100.
Okay, thank you.
Okay. And Bob, F4G Golf Sierra Whiskey has been asking if the software can be operated on a touch screen only device. So if you have a device with only a touch screen, is that possible, or do you need a mouse and a keyboard?
The first time I began working on the software, I actually managed to run it on my mobile phone, and the controls were designed so they were easier operated just by using the finger on the mobile phone's touchscreen. But as it evolved, I kind of gave up on that idea because there are currently some open source projects, like for example the KDE Plasma project, which is supposed to give a very nice touchscreen interface to be used on mobile phones and tablets, and in order to make it make the usability better for the application on such interfaces as touchscreen, I would say would need to implement the custom KDE controls. KDE is a desktop environment for Linux. If you're not familiar with that, it's like an alternative to GNOME and LXDE and more desktop environments. But KDE Plasma itself is focused especially on mobile devices. Hope that answers the question.
Okay, very interesting. So, Jean-Michel, do you have any questions?
I would certainly second your consideration about remote control, which is certainly the most attractive aspect of this presentation. And following Barry Durden's presentation yesterday on ZeroMQ streaming, I find it interesting here to see all the protocols that have been implemented for this remote control. So certainly a very interesting development on top of GNU Radio used here as a library as the base of this software. So thank you for his presentation. Yes.
Sure.
Well, I also have a short question, which is about timing once again. So we've seen the Kiwi SDR, which is based on OpenWebRX, and the Kiwi SDR has a very interesting feature, which is time difference of arrival, location finding, and the Kiwi works with a GPS receiver chip on the set-top board. So, would you think this is an interesting additional development in the future, maybe to distribute? I mean, it's great if you're operating this for yourself. That's perfect. But I guess what you're interested in also is that many other people are using it. So if you're building kind of a network of those devices so that you can use the network again, in a sense of combining different signals and analyzing different signals against each other, creating correlations. Do you think creating a common time base is an interesting path of development?
Yes, it could be. One of the reasons, one of the inspirations for the voice over IP support has been a nationwide radio over IP network, which is implemented here in Romania. It's called the Raillink Network. It's basically a single calling channel on VHF in UHF frequencies. It's a project spearheaded by Cătălin Yankee Oscar 7 Golf Quebec Zulu. And it's got over 200 repeater and simplex nodes operated. So it's all IP network-based infrastructure, and basically by activating a single node or repeater, it will open all the nodes in the country, and you will be heard all over the country just by using a portable small-size terminal. But it's got some problems like peak usage. So basically, because it's a single voice channel, on peak capacity times, let's say it's a bit crowded. So that's like an opportunity for logical channel separation and perhaps using a different multiplex access. So basically, I'm doing some investigation of using. Also, using SDR for multiplexing multiple logical channels, and also maybe using digital voice codecs over radio. But your idea about you can compare the times of arrival. Obviously, at the device, because you also have to multiplex the IP streams together, and IP streams will have their own latency. But you can basically add metadata to the streams which are received by the device. Add the metadata, and then when you're doing the demultiplexing at the remote station, then you can compare the times of arrival. So yeah, that's an interesting idea. Never occurred to me that it could be used for that. I'll think about your use case. It sounds. What exactly purpose would you have that in mind? Like measuring, I don't know, the path, multipath taken by signals, or?
Yeah, these multipath signals, where they come from, that's interesting. Analyzing the spectrum, where a station is interesting. Well, intruders to our bands find where they are. That's also an interesting application. There are many interesting things. I mean, very often the question is, where is a station? Where does a station come from? So
I think you can do that as long as you add metadata at the receiver and then multiplex. You send the IP stream to a central location, and then you demultiplex and compare the metadata that was added by the receiver when the stream sample was first captured. So yeah, it's definitely possible. There are some latencies involved because my application unfortunately uses a lot of buffers. It's an engineering trade-off between having less audio interruptions and more buffering. Basically, adds quite a bit of latency on the order of maybe 100 to 100 milliseconds, but it's doable. What you're suggesting, as long as the signal, the path delay of the signal is more than that. I would think about your use case. It's an interesting use case. It never occurred to me.
Okay, excellent. So we would have two more questions here in the chat, but we need to continue. We have the next talk right in the queue. Thank you very much, Adrian, for this interesting talk and the nice discussion. And we'll have you in the panel later on, so we can go deeper into these questions in the panel. Okay, thank you very much. The next speaker. Thank you.